Hello and welcome to part 3 of this introductory course to factorial survey experiments. In part 1 and 2, we have learned about the principles underlying factorial surveys and about different steps in designing and conducting a factorial survey experiment. Now, I will show you some practical examples using data. This part of the online course focuses on checking the data quality and how to analyze and interpret the data obtained from factorial surveys. It is not necessarily required that you have prior knowledge of data, but prior knowledge of any other statistical software, for example, SPSS or R, would be desirable. I will first give some background information about the data we are using, which is also listed here in the syntax file, which we are going to use for the analysis later. This file will also be provided as supplementary material. For the practical examples, we will use data from the EDIPOLU recruiter survey, which can be used for scientific purposes and can be downloaded from here. The EDIPOLU project aimed at examining the impact of certain applicant characteristics on recruiters' hiring intentions in Luxembourg. I jointly developed the experimental design together with my former PhD supervisor, Robin Samuel. Detailed information on the experimental design, the recruiter survey, and the codebook can be found here. The vignette universe of our experimental design comprised 36 different vignettes, which we all used. Thus, no vignette sample was drawn. However, we did use a D-efficient blocking technique to divide the 36 vignettes into 6 vignette sets, or decks as they are called, each including 6 vignettes. 3 experimental variables were included: gender, unemployment, and the nationality of applicants. The vignettes looked like hypothetical CVs, like I showed you in example 3 in the first part of our online course. Each respondent was randomly assigned to one vignette set or deck, and the order of vignettes across respondents was randomized. We used a personalized experimental setup in which each respondent was randomly assigned to one unique vignette set before the data collection. However, as already indicated, we will not focus on creating the vignette sample or merging the setup and respondent data, as this is out of scope of the short introductory course. You can find more practical examples, however, that are not covered here in the supplementary material to the book by Ausburg and Hinz, which are listed here. In the author's supplementary material, you will find example code of how to construct a vignette sample in SAS, examples of how to prepare the setup data and how to merge setup and respondent data, as well as more examples of how to analyze the data. This introductory course, as I said, is meant to give you a first set of tools to help you generally understand what is important when analyzing the data obtained from factorial surveys and how to interpret the data. Relevant variables we are going to use in this exercise are listed here, which mostly comprise the experimental variables, as well as administrative variables, such as, for example, respondent ID. So let's get started. Here, these 3 lines of codes simply say that I want to store everything that I'm doing now and all the results in a text file. This line of code here simply means that I want to set the overall look of the graphs I'm maybe going to create. Once we have done all this, and after we have downloaded the data, which in my case here, I already have done that, we can upload the scientific use file of the EDIPOLU recruiter survey into data. This can be done by using this line of code. I also did this already in this case. As I said, the data already combines the experimental setup data and the respondent data. Moreover, the EDIPOLU recruiter survey covered 5 occupational fields, which can be seen as separate experiments. For this course, I will therefore focus on data from the catering field for simplicity. However, the analysis could also be done in the full data set, but you would need to control for the occupational fields in the regression analysis, which I'm going to show later. So first, we have to select our sample, which in this case means that we only want to analyze the data from sector 4, which means the catering field. So we're going to run this command, which can be done by pushing this button up here. Once we have selected our sample, we can start checking the characteristics of the vignette experiment. This is an important step before starting any substantial analyses. For example, you want to check whether the randomization has worked, meaning whether the correlations between vignette dimensions are minimized and whether the vignette levels occur with more or less equal frequency. So let's have a look at the frequency of each deck first. In our case, there are 6 decks in total. The variable containing the decks are called decks or vignette sets. And by typing this line of code, we can look at the frequency with which each deck occurs in the data set. So here in the output window, we can see that each deck, so deck 1 through 6, occurs with more or less equal frequency, although deck 5 occurs less often than the other decks. Similarly, we can check the frequency of each vignette in our data. We can do this by running this line of code. VigID identifies each of the 36 vignettes. Again, in the output file, we now see the frequencies of each vignette, and we also see that, again, the results look good. Each vignette occurs with more or less equal frequency. Next, we can check whether the randomization of the order of vignettes across respondents has worked. One way of doing this is to look at the bivariate correlations between the vignette position and the vignette ID and vignette set respectively. We can do this by running these 2 lines of code. So the first line of code says that we want to have the pairwise correlations of these 2 variables. The first one indicates the vignette position, and the second one, as we already have seen, the vignette ID. And we want to show the significance levels at the 5% significance level. By running this, we see a correlation coefficient that is very close to 0 and not statistically significant. Again, for the correlation between the vignette position and the decks, we can run this line of code, and we see a correlation of 0. Which is also not statistically significant. We can later control for the vignette position our regression analysis to control for any possible order effects. Next, we can check for level balance. To do that, we look at the frequency of each level of the vignette dimensions. In our case, we have 3 different experimental variables: vignette gender, unemployment, and nationality. Gender is already a dummy-coded variable in our dataset, means 1 indicating female and 0 indicating males. And we have 2 categorical variables, unemployment with 3 levels and nationality with 6 levels. So first, we look at the frequency of male and female applicants. As you can see here in the output file, they both occur with equal frequency. Similarly, we can check for unemployment, and again, as can be seen here in the output window, we see that each level of the variable or the dimension unemployment occurs with equal frequency. Finally, for applicant nationality, we again see here in the output file that all the levels of this variable occur with equal frequency in our data. In the next step, we examine the bivariate correlations of vignette levels. To do that, we first need to calculate dummy variables with the values 1 and 0 for each level of our 2 categorical vignette dimensions. This can be done in Stata by running this line of code. This code will again show the frequencies and then secretly add new variables to our data set, which are listed here at the lower end of this panel, which now are dummy variables for each level of this variable. We can do the same for nationality. Then we can calculate the bivariate correlations. This can be done running this line of code, which looks very similar to the one we already used up here. However, now referring to the bivariate correlations of all the levels of our vignette dimensions. We run this code. Unfortunately, the table is broken up into 2 lines, but overall, as we can see here, All the bivariate correlations are really close to 0. They are smaller than 0.1, and none of them are statistically significant, which is what we would want. Since we use the full factorial, in this case, all vignette dimensions and levels had a correlation of perfectly 0 and perfect level balance in the experimental setup data. However, it is to be expected that we might observe deviations from perfect orthogonality and level balance in our case, due to refusal by certain respondents to participate. This is because, as I have mentioned, the randomization was done before data collection. Thus, in a small number of respondents, we might observe some correlations. Nevertheless, this does not necessarily result in no data quality. Similar to designs where only a vignette sample is used and not the full universe, deviations from perfect orthogonality and level balance are expected. The deviations, however, should be relatively small in the ideal case. All in all, our data therefore looks good, and we can conclude that the experiment has worked. Lastly, we can inspect the distribution of vignette evaluations. In this case, the vignette evaluations are the recruiters' hiring intentions, measured on an 11-point scale ranging from 0, practically 0, to 10, excellent. So far, we did not consider missing values in the data because we wanted to check whether the experiment has worked. Respondents who did not participate in the present survey were still assigned a vignette set, and it is therefore useful to include these respondents when assessing whether the experiment has worked. However, the vignette evaluations have some missing observations. From the codebook, we know that value -9 indicates non-response. So we will first recode these observations as missing values, which can be done by running this line of code. We can then show a frequency table or respectively draw a histogram to inspect the distribution of vignette ratings in our sample. First, we look at the frequency table. This can be done by running this line of code. The variable vic_eval_1 indicates our vignette evaluations. We can see that we have 300 valid vignette evaluations, 308 in our data, and that respondents use the whole answer scale, which is what we want. Then we can have a look at the histogram, which can be done by running this line of code. And we get a nice graph. Here we see that the evaluations tend towards higher values on the rating scale, and thus the distribution of vignette ratings is slightly left skewed. Okay. After checking whether the experiment has worked, we can start with the analysis of our data. As we have learned in part 2 of this online course, with mixed designs, the data is hierarchically structured. The vignette evaluations of applicant characteristics therefore comprise our observations on the level 1, the individual level, so to speak. These vignette evaluations are nested within respondents, which are on level 2. Thus, the vignette evaluations within one respondent are not independent from each other, which is, however, the assumption underlying ordinary least squared regression analysis. The standard errors of standard OLS regression would therefore be biased, and we need to account for this clustering in our data. This can be done by estimating OLS regression using robust clustered standard errors, or by estimating multi-level regression analysis, which are essentially random effects models. Multi-level modeling separates the error term of the regression analysis in 2 parts, one for level 1 and one for level 2, to account for the clustering. Due to the experimental design, the assumption of this type of models that the variables in the model need to be uncorrelated with unobserved characteristics is true for the level 1 variables by design. Therefore, you can either choose OLS regression with robust clustered standard errors or multi-level modeling to analyze your data. We will do both in this course. Let's start with the OLS regression. We include all our experimental variables in the model and also control for the vignette position. This can be done by running this line of code. This option here indicates that we want Stata to calculate robust clustered standard errors. Okay, now here in the output window, we have the results of our regression analysis. We see for each vignette level their effect on the vignette ratings. For example, we see that 1 year of unemployment at the time of application significantly reduces recruiters' hiring intentions by 1.8 scale points. We also see that female applicants have on average a slightly higher likelihood of being considered for a job in the catering field. Since being a female applicant increases recruiters' hiring intentions, meaning the vignette ratings, by 0.5 scale points. We also see that the vignette ratings are on average lower for French and German applicants compared to Luxembourgish applicants, which are the reference group in this case. Luckily, the vignette order does not seem to have a statistically significant effect on the vignette ratings in most cases. Finally, we will have a look at the results from a linear multi-level regression analysis. In Stata, this can be done using the mixed command. This line here. Here we tell Stata to also give us the variances. And this line of code means that the data are clustered at the respondent level. And the first part here looks relatively similar to the example with the OLS regression. These are, is our regression analysis. So by running this line of code, we obtain in this part of the results window our estimates. So the effect of each vignette level on the outcome of interest, in this case, the vignette ratings, meaning the recruiters' hiring intentions. As you can see, the results hardly differ between the linear multi-level regression model and the OLS regression. We, for example, again, see that 1 year of unemployment at the time of the application reduces recruiters' hiring intentions compared to applicants who have no unemployment experience. We also see similar results for gender and the nationality of applicants. A key difference is that in the output of the multi-level regression, we now see two variances. This one here, one is the variance at the respondent level, and this one here is the variance at the individual level, meaning the vignette level. As I have explained, this is because multi-level models separate the error term in two parts to account for the clustering in the data and to compute correct standard errors. However, this is mostly of interest if you want to analyze the variance at each level. At each level, as you saw in these examples, you can also use OLS regression with robust clustered standard errors to interpret the results of your factorial survey experiment. Okay, this was the last part of this introductory course on factorial surveys. I hope I was able to give you some idea of how to analyze data and check for the quality of the data. Of course, some aspects of the research process could not be discussed in detail within the scope of this short introductory course, but I hope that I was able to provide you with some good starting points to create your own research projects around factorial survey experiments. As I said, you can find additional references on some of the issues we have discussed in this course and beyond in the recommended reading list in the supporting material of this course. Thank you for your attention and have a good day.